So let's say we had this aqueous solution of water. We learned in the previous video that these water molecules are going to react with themselves. They're going to autoionize, forming some hydronium and some hydroxide. And we also learned it's this hydronium ion concentration that determines the pH of the solution. That's all we need to know to determine the acidity and pH of the solution. If we have a high concentration of hydronium, we have a very acidic solution with a low pH. If we have a low concentration of hydronium, we have a very basic solution with a high pH. So again, we know all we need is the hydronium ion concentration and we can determine the pH of the solution. And we know they're related using this equation. As long as you know the hydronium ion concentration, if you plug it in this equation, that'll spit out the pH and the acidity of the solution. However, what if we had a buffer solution? So this represents a buffer solution. And we know it's a buffer solution because, again, we have an aqueous solution with water and these water molecules. However, we also have a weak acid in the form of acetic acid, and we also have its conjugate base, acetate. And something important to realize, this is just something you just simply need to memorize, is whenever you have an aqueous solution with a weak acid, and you also have some of its particular conjugate base, then you have a buffer solution. And this is a buffer solution because it buffers changes in pH. So therefore it buffers any changes in hydronium concentration because, again, it's this hydronium ion concentration that determines the pH of the solution. And we'll go into more detail what that means, buffering this hydronium ion concentration. But again, if we wanted to find the pH of the solution, the acidity of the solution, we know this acetic acid and this acetate, they're going to react with these water molecules. They're going to reach an equilibrium. We're going to have a certain hydronium ion concentration. And again, all we need is that hydronium ion concentration, then you can determine the pH and the acidity of the solution. However, whenever you have a buffer solution, which we have a buffer solution, there's another way to determine the pH of the solution. There's another formula you can use to determine the acidity of the solution. And that's this equation, this Henderson Hasselbalch equation, where again the pH of a buffer solution, this only works if you have a buffer solution, equals the pK of the acid in the conjugate acid-base pair. So you need to know the pK of the acid in the base pair, plus the log of the concentration of the base divided by the concentration of its conjugate acid. So as long as you know the pKa of the weak acid and you know the concentration of the base in the conjugate acid, then you can determine the pH of the solution. So there are these two different ways to determine the pH and acidity of a solution. But again, this is a buffer solution and this is not a buffer solution. So why? What's going on? Why is this one a buffer solution and this isn't? Well, let's do an example. Let's say we added some hydrochloric acid to the solution. We know this hydrochloric acid is a very strong acid. So what's going to happen when we add hydrochloric acid to the solution? Well, we know it's going to protonate some water. It's an acid, so it's going to protonate some water, and when it protonates the water, it's going to create some hydronium. So now we're creating hydronium, we're increasing the hydronium ion concentration, so we're creating a more acidic solution. So as we add this hydrochloric acid, this solution is going to become more acidic. And again, we know the hydrochloric acid is going to react with this water using this equation, and a product is going to be this hydronium. So we're going to create hydronium, and we're going to drastically change the pH of the solution because we're going to create a lot of hydronium. However, what if we were to do the same thing to this buffer solution? What if we took this buffer solution and added some hydrochloric acid? How will that change the hydronium ion concentration and affect the pH of the solution? Well, notice we have this base. We have this base that's sopping up all these hydrogen ions. So when we add this hydrochloric acid, instead of protonating water, we have this base kind of sopping up all those hydrogen ions. So instead, we're going to go through this chemical reaction, where again, this base is going to sop up all those hydrogen ions. So when it sops up all those hydrogen ions, it forms this acetic acid, this conjugate acid, which is a safe, neutral form of this hydrogen. It's storing that hydrogen. So now, because before in this situation, when we add the hydrochloric acid, it protonated the water, and when it protonated the water, it created hydronium, and therefore changed the hydronium ion concentration and made a more acidic solution. However, this example, we're buffering, we're preventing that. This is stealing those hydrogens, so therefore this hydrochloric acid doesn't have a chance to protonate water, so therefore it doesn't have a chance to create hydronium, so therefore it doesn't have a chance to change this hydronium ion concentration, and it can't affect this hydronium ion concentration, so therefore it can't affect the pH. So that's why this is a buffer solution. Because again, in this situation, when we add the hydrochloric acid, it immediately protonated water, creating hydronium, and therefore creating a very acidic solution. However, this solution buffers changes in hydronium ion concentration, so buffers changes in acidity. Because instead of being able to protonate water and creating hydronium and creating an acidic solution, instead we have this base sopping up all those hydrogen ions. And when it sops up those hydrogen ions, it stores that hydrogen in a safe form, in this form of this acetic acid. And in reality, it's a little more complex because this acetic acid, it's also an acid. So it will protonate a little bit of water, but again, this is a weak acid. It's such a weak acid that, in fact, it will actually protonate very little water. Out of nearly every 1,000 acetic acid molecule, only one of them will protonate a water. So when we protonate this conjugate base, forming this acetic acid, it's a pretty safe, inert, stored form of this hydrogen, so therefore we're not able to protonate water, so therefore we can't create hydronium and create a more acidic solution. So that's why this is a buffer solution. But we also, remember I said we have a buffer solution when we have a acid and its conjugate base. So for a buffer solution, we also need this acid, this acetic acid. So why is that important? Well, let's do a different example. Now, let's say we added some hydroxide. So in this example, with the non-buffer solution, what would happen if we add some hydroxide? Well, we know that hydroxide will deprotonate water, and it will also deprotonate hydronium. So therefore, through an equilibrium, we're essentially decreasing the hydronium ion concentration, so we're creating a basic solution. So if we add hydroxide to this solution, we would create a very basic solution. However, what would happen if we added hydroxide to this solution, this buffer solution? If we added hydroxide to this buffer solution, would we do the same thing? Would we deprotonate hydronium and water and therefore creating a more basic solution? Well, no, because again, it's that same idea. We have this acid. So when we add in this hydroxide, we have this acid protonating this hydroxide. It protonates this hydroxide, this base, essentially neutralizing this base. So now we don't have a chance to deprotonate water or hydronium, so therefore adding this base, we don't have an opportunity to change this hydronium ion concentration and change the acidity of the solution. Again, we would essentially go through this kind of chemical reaction. So again, in this example, with the non-buffer solution, we add the hydroxide, and we essentially wreak havoc. We react with these compounds, essentially decreasing this hydronium ion concentration and making a less acidic solution. But in this buffer solution, when we add the hydroxide, instead of being able to change this hydronium ion concentration and deprotonating these guys, we have this acid protonating this guy, essentially neutralizing this guy. Again, it's protonating this guy, neutralizing it, so now we don't have a chance to deprotonate these guys, so therefore we're not affecting this hydronium ion concentration, and we're not affecting the acidity of the solution. And again, it's kind of the same idea. Once we protonate this acid, yeah, we're left with this conjugate base, but again, this is a weak base, so therefore it's not having a really big effect on the pH. And something else important to realize is we have a buffering capacity. For example, maybe we have 1 molar of this guy and we have 1 molar of this guy, but what if we added 2 molar of this hydroxide? Then when we add 2 molar of hydroxide, 1 molar of this guy is going to be deprotonated. So once that 1 molar is deprotonated, now we still would essentially, if you did the stoichiometry and math, we would have 1 molar of hydroxide left, and now this 1 molar of hydroxide would be able to affect the acidity of the solution. So therefore, this buffer solution has a buffering capacity depending on how much base and conjugate acid. But again, maybe if we have, again, this buffer solution and we added 0.5 molar of this hydroxide into the solution, then again, we essentially would deprotonate some of this acid, but we would have enough acid to essentially neutralize this hydroxide, so it would buffer the solution. So again, this is the Henderson Hasselbalch equation, and the point is this is a buffer solution because it buffers changes in pH, because it buffers changes in hydronium.